So as we said, we are moving forward with the top selected classifiers, which is going to be part 5, as mentioned. Last week, we looked into decision tree, looking at it, what is decision tree and how decision tree works. Then we try to look at the example today. So we define decision tree as made up of a system that is able to build either classification or regression model in the form of a tree structure. And I alluded to the fact that decision tree is very, very common because in our day-to-day activities as engineers, as educators, even home analysis. When you want to divide things into groups, we always want to do the analysis. It's very simple. Okay, if I want to buy something, this is here. If I buy this one, I go here. When I finish this, I go here. This is a kind of a natural way that people like to solve problems. That's why decision tree comes up. Tree structure analysis base comes from a different aspect of our daily endeavors. So it is based on this also principle that we have the decision tree in machine learning. So whereby, for example, you can easily have, here it's known as the root node, the beginning. From there, you take decision, and then some people will come here, some will be here. When you've done with this, you keep going until there's nothing to work with. We say this is root node, this is decision node where you take decisions. Decision node could be as many as possible, but in decision tree, when we want to, our idea or our aim is to optimize it so that we have lesser decision nodes. The lesser you have before you get the final result, the better. The more you have, the more the trouble. So that's why later we're going to talk about how do you optimize it to make sure that you select the correct node, because the node you start with will determine how many decision nodes you are going to have. If you choose a wrong node, you can keep going infinitesimal. You see, however, if you select the appropriate nodes to start with, within 2 or 3 decisions, you'll be done. So it has the root nodes, it has the decision node, and the leaf or terminal nodes, at which point you finalize that particular point. We also talk of different types of decision trees, a model that could be built, it could be classification, and it could be regression, even though it is preferable to use decision tree for classification because of the complication that are associated with using it for regression. It's not impossible, but it's not a preference. Yeah. So we gave example of this last week where we discussed it extensively. So trying to see how you can build it as an example, build different versions. Then we describe the concept of a classic decision tree as a tree induction system. So, and then we finally also look at the example from that point of view. We give example of how you can build a tree like this. If you select the age, you can see just immediately you choose the age. Either you are youth, you are middle age, you are senior. See, this is a decision. This is a decision node. But you can see here, immediately, just by one decision, we reach the terminal node here. So it means age is a very good option to quickly get to where we are going. If you choose credit rating, we analyzed it last week that you might not be able to end the decision tree as fast as it has been done here. So, and then we move into algorithm for decision tree last time. So we said decision tree algorithm is a greedy algorithm. Greedy algorithm in the sense that it uses what we call top-down recursive divide and conquer. It's one of the algorithm technique that is often praised, divide and conquer. You need to make sure it's not used against you. Because anyone that uses divide and conquer will definitely likely going to win. So you see, divide them, conquer this one, go back to that one and conquer it, then you mic them together, you get your final solution. So this is the principle of decision tree. And in real life, it works greatly. So you start at the beginning, as you go down, you keep bringing them down into groups, and then you're solving them, and then later, finally, everything gets combined together. So now we're going to revise the algorithm together. So the tree is constructed in a top-down recursive divide and conquer manner. So at the start, all the training examples are at the roots. See, all the training examples are at the roots. Then you have the attributes, which are categorical. If they are continual value, we need to discretize them. We also explain this concept of discretization. Usually, attributes that are categorical is straightforward. For example, you have gender. So it's either male or female. So you can easily categorize it, but when you have age, some people are 60, some 70, some 120, some 150. So in number, you have to kind of discretize it. Okay, I'm going to consider them less than maybe 70, less than or equal to 70. And the second option is going to be greater than 70. So in that case, you see, you can easily partition them to where they belong. This is called discretization. So where you can change continuous value to become more like a grouping, a categorical system. So it's either you are, so even though these are numbers, so we can make them to now become, this one is going to belong to this side. 70 also belongs to this one. Why this one and this one will belong to this one? This is called discretization. So you have to discretize if you have continuous variables before you build a decision tree, as we are going to see in an example now. So the examples then are partitioned recursively based on selected attributes. So you divide it. So once you pick an attribute, where do you belong? Is it male or female? Then you categorize male to the left, female to the right. If you go to that side, if there's need for also another partition, you keep doing that recursively. Recursive means the algorithm is going to be calling itself to come back again and divide and conquer. Usually divide and conquer is really like out of recursive. You keep dividing and conquering until there's nothing to divide, or the problem you want to solve is done. All the samples are already consumed. This is why we now describe then the test attributes are selected on the basis of heuristic or statistical measure, which we call information gain. So when you build the first three using this attribute age, how do you know the attribute to use next to building it? We also described this extensively last week. How do you know the next attribute to take? You see weight or the length of the famous, depending on the problem you are solving. So we use something called information. Sometimes we use heuristic, common sense, rule of thumb, based on your experience. You just try to say, okay, I can use this based on my experience. It's going to work faster and better. But however, information gain is a better way to do that. And we're going to see how do we implement information gain. And then we have the condition for stopping. Since it's a recursive system, it continuously iterates until any of these conditions or all of them or one of them are met. Either all samples for a given node belong to the same class. So when all samples for a given node belongs to the same class, that node, you don't divide it anymore. That is, you finish working with that node. You go to the nodes that still has both classes in the same node. Because the idea is that at every point in time, we want to have the final nodes of a particular junction that belongs to one class. So, or if there are no remaining attributes for further partitioning, sometimes, even though the samples are not yet totally classified, but there's no more attribute you can select. See, and you don't repeat attributes in this sense. So in that case, you have to employ the concept of majority voting to classify the leaf nodes. Because here you are going to have leaf nodes that are having mixture of yes and no, both classes. So we have to have majority. So what are the majority class in that particular node? Then you assign them to that particular majority class. Now, and then, or another option is there are no samples left. Of course, this is one is very obvious. If you finish classifying the samples you are given, then there's no need for you to keep trying. The system automatically ends there. So this is the algorithm for decision tree induction, which is based on top-down recursive divide and conquer. Now, so I believe that was where we stopped last week. So here today, we're going to start with this example of a decision tree. How do we implement it? Now, this is just for us to have a kind of deeper understanding of machine learning principles and concepts, especially the algorithm. The good thing is, and the good news is that, except for those people that are mathematical oriented or that really want to have an inside how it really works. For many people, they don't really need the details, actually, because I need to clarify this for you. So you have systems that have been implemented for you. But sometimes, you just want to understand how the thing is going on inside so that it doesn't look like a magic to you. So as we are going to see later, we are going to open Weka. You see how you can implement decision tree. Just a few clicks of mouse. Open, click, set your data, run. It will run your decision tree for you. How do you write the code for the decision tree? You don't need to bother yourself about that. Even if you are using Python, You don't need to go and write your code about decision tree yourself. The codes are available for free. See, that is something unique about machine learning, because what they are interested in, how can you make use of what is existing to really solve your own problem? So, however, just once in a while, we decide to take algorithm, go in depth, so that at least we have an idea what is going on inside the machine learning algorithms. So this to classify, kind of clarify for us, in case maybe anyone find it a little bit tough or challenging to follow. So we're gonna talk a few mathematical bases like probability also, so which are also very simple. But then, you know, some people are not mathematically oriented; they might find it a little bit challenging. So don't worry, note down your question. We will revert back to you at the appropriate time. Now, so I say that to let you know that you don't really need to have in-depth knowledge about what is going on inside before you can use machine learning. It's just like a tool. It's like an Excel. It's an Excel sheet. You know, there are so many behind the scene detail about Excel that you don't need to know, but you use Excel on a daily basis. But if you really want to know it, then you can go inside and know it. And that's why we're not going to be spending too much time on this kind of detail exposition for some time. So, but then once in a while like this, it's good to have an in-depth understanding of few of the, like I was saying, this is an example of a decision tree problem. So we have, this is a data set. We call it training data because you need the training data set to be used for building the model. So when you finish building the model, then you can bring in the testing set to check if your model is performing well or otherwise. Now, so in this data set, we have three attributes. Attribute number one, which is categorical. It means you can see yes, no, yes, no. There we have categorical. The second attribute, marital status, which is single, married, single, divorced. So these are called categorical attributes. Then we have the continuous attributes, like taxable income, the amount of money you have that is taxable as income. So these are in numbers. This is called continuous. So this is the one I mentioned earlier that you need to discretize them before you can use it in decision tree. Now, so to solve this problem, then the class is you want to decide who among these particular personalities will be involved in cheating at a point in time. So we want to decide, okay, this is no. If you're able to make a refund, yes, the refund is yes. Is single, is taxable income is 125K above, it's not likely to cheat. It's not likely to cheat. You can see, yes, if there's no refund, the taxable income is 95K, is divorced, it's likely to cheat. You can see some of them. This one is no, it has no refund, is single, 85K taxable income. Yes, it could also be involved in cheating. I mean, these are kind of information from historical data. Now, we want to be able to build a model that can categorize this. Now we know the target. This is why we call it train set. We know the target. So this target is going to guide us on how we're going to build our model. So once you finish building the model, then someone can give you now a totally new sample that is not air, and we'll ask you to tell us, is it going to be involved in cheating or not? Then you have to be able to use your built model to solve that problem, as you are going to see shortly. Now let's start the building. You know, you have the option to select from any of these attributes as the starting point. You can, if you like, you can start taxable income as the first one. If you like, you can start this one as first one. If you like, you can start this one as one. You can start at random. If you like, however, you should know that the attribute you start with will determine the kind of output you are going to get. So, and that's why later we're going to talk about, instead of doing it at random, there's a system to do little calculation and use that calculation to tell you which of these attributes is better to be selected. We call it the entropy and then the information gain. If I use refund, what's going to be the information gain from it? If I use marital status, if I use taxable income. So those information will guide you to know the best one to be selected. But for now, let's do it at random or select one by one. So and see what's going to be the outcome. Now let's start from refund. So I pick refund as my choice of attributes, first attribute. So this is then we're going to call it the root node now. This is the root node for us, the root node. So in the refund side, so you look into, now since we are dealing with refund, these are samples. Look at the value of these attributes, of this, the value of this attribute for each sample. This person has a refund, yes. This one is no, this one is no, this one is yes. So since refund has only two values, yes or no, so it's going to have this divided into just two. You can see here, refund, yes, no. So in that case, yes, no. Everybody that has yes on refund, we automatically will put here. See, anybody that asks, when you say yes, you see, when you say yes, this is yes. You can see here you have no. See, yes, no. If you see yes, no, yes, no. This means that actually refund is a very, very good attribute to start with, because once you partition the data into two, immediately it produces terminal nodes. This is a terminal node. Very rare to get terminal node from just first testing. You see, usually you expect some miss at some point in the other. So this one gives us terminal node from the left side directly. So it means it's a good way to categorize these people, that anybody that has yes as refund, I don't need to care about the value of marital status or taxable income. Automatically, that person will be categorized as no. You don't cheat if your refund is yes, because this is what the data is telling us. Yes, yes. But if you look at no, you know that it's not the case. If you look at this is no, no, you can see no, but some no here is having yes. It means the no side is having mix of yes or no target class. This is the target class. This is the class we want to predict. We call them target class, or the output to be predicted. So that's why we are not going to do anything here, because everybody that comes to this place now, they are automatically no, confirmed. It means we successfully remove 3, 1, this is 1, 2, and then 3. So these 3 samples out of 10, they are automatically removed now. They are classified. So we build this model as such. Anytime we have a new sample that is coming in with yes as value under refund, we don't need to waste our time. Automatically, we push that person to be no. The class prediction is going to be no for that sample. This is how it works. However, for the no side, we have to go further, because in the no, you can see there's mixture of yes or no output. Some people could be no under refund, but yes, they have no. While some also they have no, they still have yes as output. In that case, we cannot decide yet. So we look at the next attribute to be selected now for breaking them again into 2. So the choice is to choose marital status. In marital status, you have single, you have married, you have single, you have married, you have divorce. Married, you have divorce. See, now, this one could be solved in a kind of, one heuristic could be used here, because it's single and divorce, because we don't want to break it to 3. You see, usually we go 2, 2 at this point in time. So we can assume that, okay, let's pick single and married, single and divorce. Let's group them together, because in reality also, divorce is also indirectly single. Of course, it has a special status that it was married before. Now, we'll come back to that later and see the analysis. So we divide into 2, married, then single or divorce here. So it means, look at everybody that has marital status as married. Married, you can see is no. Married is no. Married is no. Married is no. This means it's a good way to go. Everybody that is married has no as the target value here, the target class. So in that case, we also have a terminal node. So the idea of decision tree, that's why we say it's a greedy algorithm. We want to get terminal node as soon as possible. The faster you get terminal node, the better. So it means here we have terminal nodes. So which means if you give me a new sample later that has a refund no, but marital status to be married, automatically I'll classify it as no. It's done. So now I'm left with single or diverse, and then I need to divide. Then I'm going to look into the taxable income. The taxable income, now I have to discretize. See, this one also need your kind of experience, or you look at the data. You discretize, we decide to say, okay, is your taxable income less than 80,000 or greater than 80,000? This is the yardstick. So if you are less than 80,000, you be no, because it is studied here. You see, everybody that is less than 80,000 is no. This is no. This is no. Yeah. So if you are greater than 80,000, most likely it's going to be yes. So you have some people that will be in between. This is just an example. Now, this is the model we have built for this kind of solution. Now, quickly, don't forget, I told you there is different way you can build it. We can also build it in another way. This is the same data set, but now we started with marital status. So with marital status, we build it just like the way we did. You can see here we got married. We went to refund, no. Then we went to taxable income. Say there could be more than one tree that fit the same data. This is just the idea, just established. There could be more than one. If you start with different attributes, you get different model. This is the idea. However, sometimes, especially if the problem is a little bit complicated, so you have to, it's better for you to use the special calculation we use to check which of these attributes might give us better result. Because here we are looking at it physically to say, okay, which one should we choose? Imagine you have like 1,000 data set. It might not be possible to easily visualize them as we try to do. So that's why we have to use such method as we are going to also describe. Now, so having done that, so this is the training set we have used. We call it induction. If you remember when we introduced ourselves to the concept of training and testing, it's like doing an induction. Through the induction, we're able to build the decision tree now. You see, we're able to build the decision tree, which we call the final model, decision tree model. Now, the testing set has been provided for us. You can see now, they gave us now new samples. We use 1 to 10 for training, which is building the model. They gave us 11 to 15 now. The class now is missing. Now you need to use the model you built already to push this one to tell us the class. What is the class of this? What is the class of this? See, for people doing something in the laboratory, you give us enough, you get enough data for training. Once you finish with training, next time you're going to do experiment, you don't need to waste your time in the laboratory. Just give us the values. The system you have built, we predict the outcome of what we are supposed to get in the laboratory. You see? So once you're able to test the test data, actually, in the test data, we have the output, but we have to hide it from the system. We know the output because this is testing data. We know the output, but we don't give it to the system. We want the system to use its own built model to tell us the outcome of each of these samples, as we are going to see as an example. Now, let us apply the model to a test data now. Let's apply it to a test data. Now, this is test data, which is, I think, is number 1 in that, yes, yeah. Just a minute. Now we build the model already. So let us now use a test data to check the model we already built. So we have to start from the root nodes. Since we decide to pick this model, you might also pick the second model, which the one that started with marital status. You can pick anyone, depending on the model you have used. You have to, yeah, whatever model you decide to build. Now, since this is the model we have selected, this was the first one we built. Now you start from this root node, you look at refund. Refund is no. For this, we don't know, maybe it's going to shit or not. We want to predict. This one we want to predict. Okay, refund is no. So we go to root node. When we have refund, yes or no, it means no is here. If it were to be yes here, assuming we have yes, let's say we have yes, automatically we say, okay, class, we predict the value is going to be no. But unfortunately, it is no. So we cannot decide at this point. We go down, this is no, it comes to this side. It means we are done with the attribute refund. So we go to the next attribute, which is marital status here. Marital status is married. So we come here. You can see here, single or divorce is to the left. Married is to the right. And then immediately you have married. This is the output, the predicted class. So we don't need to check the taxable income anymore. You see, we don't check the taxable income. If you have like 20 attributes, 20 more attributes, but you are able to get one of these attributes value that has a terminal node directly after it, then you stop. You don't need to start checking others. This is why I said the choice of the attribute in building your decision tree model is very, very important. If you choose a wrong attribute to start, then the model is going to be longer before you start getting the result. So it means after 2 steps now, we were able to classify this one to be no. So this one is not going to involve in cheating. And then you can then apply this to as many as possible test data that you have. So this is how you build a decision tree model, and how you can also apply the built model to the test data. See, so you can see this is the path we follow. We took this one, refund, it's no, it's here, married is this. So we assign this one to the output straight. So assign sheet to this particular value. So what happened to this? Because our data, we got our data classified before we even reach that side. There could be other example that you need to get to this place before you actually get the final result, depending on the kind of samples you are given. That is how to apply the model. Now, so as we have seen practically, how does it really work? In 3 steps. We said step 1, you pick the variable that gives the best split based on lowest Gini index. So I'm going to see how do we calculate the lowest Gini index. You do some little calculation to get the lowest Gini index. You go for that particular variable that will give you the lowest. Then step 2, partition the data based on the value of the variable, just as we have demonstrated. We choose refund, partition it to left and right side. Then step 3, repeat step 1 and 2. This is why it is recursion. You keep repeating it until any of the 3 conditions are met, which I mentioned earlier. You keep repeating until any of the conditions are met. So having done this, so this case step will keep repeating itself until the 3 conditions, which I mentioned earlier. If you remember, these are the conditions. Either all samples of given node belong to the same class, or there are no more remaining attributes for further partitioning, or there are no samples left. You keep going until any of those things happen. So it's a very simple 3-step problem and algorithm. Now, we say splitting stopped when CAT detects the name of the popular algorithm for decision trees known as CAT. There are several other of them. So it detects no further gain can be made, or some preset stopping rules are met. Alternatively, the data are split as much as possible, and then the tree is later pruned. Sometimes you might need to keep going with the data. Some data really depend on the data set. Always remember my saying, let the data speak. So it depends on the data set. You might have some data that within 2, 3, 4 steps you are done. While in some data set you keep going, the tree will never stop, especially if the data has noises or outliers. You keep breaking them down, depending on the size of the data and the size of the attributes. So later we might do what we call tree pruning. You know, it's like practical pruning. You know, when you plant flower in your house, because a decision tree is from tree. The tree is just like this, shajara. The tree is like this. So the same way in decision tree in machine learning is embedded. So it's just a tree, it's like a tree. So when you have your flower in your environment, if it's grow too much, what do? You prune it, you cut it away. You're gonna cut some of the excessive side of the tree so that it doesn't fall on your house. The same thing we do when you have decision tree that are too much long, then there are some principles you have to prune them. You have to cut some irrelevant. There's some data so you know that this is an outlier. Outlier is a data that is totally out of range with other data sets. So they can distort your model. So such kind of data, we cut it off. We prune the tree to have a reasonable tree. Of course, this is depending on the kind of data that you have. Now, this is a practical example for another example for this. So we have predictors, we have targets. So we're going to demonstrate how we can calculate the algorithmic value, the gaining index to know which of them should I start first. So let's look at the data together. These are the predictors. Remember, predictors are the same thing as attributes. We use a lot of terms interchangeably. Predictors are called attributes. So they are also called the independent variables. We also call them features. So let's pay attention to those names, okay? They are the same thing. And then I clarify. So the targets, people call it output or prediction target. That is the value, the attribute to be predicted, or the output. However, I clarified last week that some people used to call molded, when they build a model, they say we build a predictor. No, you don't build a predictor. Predictor is the attribute, because the attribute, actually the model, you use the attribute and the target to develop your model. So the model is not called a predictor. You can call it prediction model, which is a model for prediction, but not a predictor. You see, so sometimes we use English. So if you call it predictor, you are not talking of model, you are talking of the attribute already. So we take note of that. Now, these are the attributes given. We have outlook. This is the outlook of the day. We have temperature of the day. We have humidity of the day. We have windy. See, you want to decide if somebody should play golf or not. This is going to be the next practical example we're going to use. And we're going to calculate the Gini index this time around. We're not going to do it randomly, because you see we have sizable number of attributes now, 4 attributes. 1, 2, 3, 4. So which one do we start first? Should we start with outlook or temperature or humidity or windy? Because if it is outlook, outlook could be rainy, overcast, sunny. Yeah, those are the 3 or 4 options that we have there. We have temperature, hot, mild, cool, humidity, high, normal, and then maybe normal, high, and then normal. Yeah, windy is false or true. It's either windy or not windy. Then the decision is play golf. No, don't play golf. Yes, play golf. So what are the attribute combination that makes us to decide to go and play golf? And what are those ones that are combined together that ask us not to play golf? For example, here, overcast says if the outlook is overcast, temperature is hot, humidity is high, windy is false. It's not windy, so go and play golf. Maybe being windy might be a decision not to play golf. You can see here, anywhere we have windy, true, we don't play golf. But here it is true, we still play golf. See, this is why classification could be a very challenging thing. And that's why machine learning algorithm is very, very interesting. Because you can, as a layman, you want to look at it, I want to look at one attribute that can classify all of them. You might not be able to see. You see? That's why we have to go hand in hand. One attribute will assist the other attributes. Unlike the previous example, that if you have a refund that is yes, automatically you don't cheat. Very rare to have such a very simple data. Very rare, but sometimes we have it. And again, that takes us back to let the data speak. Some data sets are so nice to you, within a few minutes you are done with your modeling, you get 100% accuracy. Otherwise, you could be on the system for as long as possible. Now, so once we have the predictor, the attribute, and then the target, then this is the decision tree we built for it. As an example, outlook. We started with outlook as our decision, the root node. This is the root node. So we have the 3 options here. So which one? We go here. You can see here from outlook, anybody who is overcast is automatically yes. Anybody who has overcast is automatically yes. All overcast, yes. This is one reason why outlook is a good one to start with. And you are going to see how we can use the entropy and the information gain to decide that Outlook is actually the best way to start. This is just showing you the result, but how did we get this particular result? We're going to go into it in details as we move on, inshallah. So we can see here, this one is having mixture of play golf, not play golf. So we have to choose another one, which is windy. Here also we have to choose humidity. You can notice that at the end of the day, we have yes, no, yes. We got to terminal nodes without using temperature. You see, sometimes it's like that. Actually, the aim of decision tree is we want to get our problem solved without wasting time. So because of the Outlook we selected earlier, if you had gone to select temperature, you will have wasted a lot of time, because it means temperature was not really a good way to separate when to play golf and when not to play golf. Because without even using temperature, we were able to separate our data set into play golf, don't play golf. See, that is why the choice of the attribute we start with is very, very important. And we are going to now see how do we really build the system. Now, the core algorithm for building decision tree is called the ID3. So developed by Quillen, so which employ top-down greedy search through the space of possible branches with no backtracking. Like I said, there's no backtracking in decision tree. You don't use an attribute 2 times. Once you use an attribute, halas, you are done with it. You don't come back to that attribute. You keep picking other attributes until you get your job done. So the ID3 uses entropy. It uses the entropy and the information gain to construct a decision tree. What we use the entropy and information gain is actually to select the next attribute to be used in the partitioning, because the aim and objective is we want to get to the terminal node at the shortest possible time interval while getting all our data correctly classified. So with this model now, if you pick any of this sample without checking the output, this model will take you to the correct output. If the outlook is raining, you go there and see raining. What is the humidity value for that? It is normal. The next thing you are going to see that, okay, is going to be yes. So this is the essence of the model. Once you build the model, of course, it doesn't mean sometimes there could be mistakes. Yeah, sometimes you cannot build model. That's why I told you in one of the stopping criteria, sometimes the attributes are finished, but then not all the attributes are classified. Then in that case, you're going to have some mistaken classification, which we can deal with as we move on. So considering our time, so this is where we're going to call it a stop for the day. So next week, inshallah, we're going to start from how do we calculate the entropy for decision tree, because the entropy and the information gain will make it easy for us without doing trial and error to know which of the attributes are better to be selected or are the best option to be selected as a starting point. And even after I finish the outlook, if I select outlook, the next thing is, how do I know I have to select windy or humidity? Why am I not selecting temperature? We have to, at every step, we have to calculate the information gain. Temperature has so much bad information gain that we decide to say, no, it's not necessary to select it. And it is clear from this state that the moment you have outlook, windy, and humidity, we got all our terminal nodes. So there's no need to have temperature. On the other way around, if I've started with temperature, I will have started with an attribute that is not important. But sometimes there's no way you can know by just looking at the data set. So like I said, we're going to start from there. How do we calculate the entropy and the information gain? And we are going to practicalize it with this same example that we have displayed. So with this, I say thank you very much for the time. And then we look forward to continuing with the classes in the next class. So now we're going to move into the next session of the class, which is question and answer, if there's any. Thank you very much, and wish you all the best.